This chapter winds up with word problems. Now, no two words in math strike more fear into students than word problems. Correctly, word problems can be very tough in math. However, I think in this chapter, at this particular moment, you won't find word problems to be much of a problem if you really pay attention to this first screen. This first screen is what we can do with quadratics right now. It's a long list, but it's not that long. So in any word problem, you're going to be doing one of these things. You just have to decide which one. Well, we'll get that in a minute. Let's just talk about what we can accomplish once something's factored. Dun, dun, dun. You see, at this point last chapter, we didn't know how to factor. So I had to give you everything in factored form. And I asked a word problem on the test that I'll basically ask again today. The only difference was it was factored. So if you want, we took a whole chapter to get right back to the same question again, but the questions won't be in factored form. Maybe it's that easy. Let's see. Recall, an equation in factored form is given by y equals a, x minus r, x minus s. Again, if these letters confuse you, then underneath write an actual equation. That's right, or over top. I'm going to put it over top. Say it was y equals 3, x minus 5, x minus 2. I just made one up there. So when they come out with these algebraic expressions that are very confusing, try putting some numbers in there. Not for the x's, for the other things, and go, well, what if it was like this? And if your brain comes back online, good. Now you're like, oh, now I get what you're saying. If I'm giving something in factored form, whoa. What's happening there? Let's get that out of there. So there are 4 things we can do. And when I marked your test last round, most people could do these things. So let's remind ourselves what we can do once it's in factored form to determine the zeros. We set y equal to 0. So the zeros are, let me say it again, when in factored form, life's pretty straightforward here. Yeah, plus 5 and plus 2 in my example. See how the example helps to go, oh, the zeros are x equals r and x equals s. And all we're saying by r and s is like, well, whatever number's there. You do whatever quadratic you're doing, but just those numbers that are there. So don't let the r and s confuse you. If you want, put a little box over the r and say, whatever's there and whatever's there. That's all the r and s is trying to do. It looks like it's trying to confuse you, but not really. So we've got the r and s. We've got the zeros. Then we could do something with those two to find the axis symmetry. Halfway between them, right? Right in between. And so actually it could be that easy. If you had them on a graph, you could just count in. I really have no problem with that. I think that's a perfectly good method to do this. But we did have a little method to do it. We did have something we could do with them to algebraically do it if you want, to do it with the numbers. Remember what we do with these? Yeah, add them 2 together and divide by 2. Really, it's just average. Like when you find your average, when the midterms come out next week, to find your average, you'll add up all your marks, but you'll divide by 4 because there's 4 marks. Well, here there's only 2 x values. So you're going to add them together and divide by 2. So I'll write this in a fancy format so you can look at it and sort of use it as a study page. X value of the vertex, I'm already giving away another answer. The axis symmetry is r plus s divided by 2. I've got to be careful with my s's. They look like 5s if I'm not really careful there. So I added a little extra loop to my s. OK. Then every time we did this question, we did the same thing. What did we do with that x value to get the optimal value, that highest y value or lowest y value, depending? Sub in. Sub in xv into the equation. I don't remember how to do that. Oh, yeah, I'm going to do a whole bunch of word problems. I don't know, there's like 4 or 5 that I'm going to do. I'm going to do that again and again. This is just like your where were we, or like your study page to look back at. And then determining the vertex, well, all the information's already there. Here you put the axis of symmetry. And here you put your optimal value. I mean, that question is like a little tricky only because it's like, what do you mean find the vertex? Aren't we already done that by the time we've done these steps? Okay, so when we're going to do word problems, this is all we can do right now. We either go, do I want the zeros or do I want the vertex? And we've got the steps to do that now. There is one nice tricky one, though, coming up. So if you're bored with all this, which you could be, if you remember what you had last chapter and what you got this chapter, a lot of this might be like, yeah, okay, no problem. But there is one spicy, we'll call it the spicy word problem. There's one spicy one coming. Okay. More time there? Oh, this only says 4 pages. I've only got 4 pages on my screen to do. To me, that means like 3 examples. Do you see 3 examples? Yeah. By the time I'm done example 1, many of you might be like, okay, I got it. Wrap it up, go sit down. I'm good. A cliff diver's height above the water can be modeled by h equals negative 5t squared plus 14t plus 3. Actually, pretty close. Well, these won't be perfectly realistic, but they're getting really close to realistic about things flying through the air. We talked about that in quadratics at the start of all this. A parabola represents something flying through the air really closely. It does it remarkably well. The only problem with it is to keep the numbers, to keep the numbers nice, oh, what's happened here? Oh, to keep the numbers nice, the numbers might get a little unrealistic as we try to keep the numbers well behaved. The only other thing that comes into play is if there was wind resistance, then this won't be perfect, but all of that's way in the future. It says, how long does it take the diver to hit the water? I think a little picture can help you understand perfectly what we're trying to accomplish. Now, I don't know exactly what this diver does. Something like that. Some kind of parabola. So if I want to know when he hits the water, that's what I want there. I want the 0. And that's why these word problems in this chapter aren't as bad as other word problems. Because there's only 2 things you can be looking for right now. There's only 2 things we can do. Find the zeros, or maybe find the maximum minimum. I'm not going to peek at B. Good chance it does that. For now, I'll get zeros. So, A, 4 zeros, set h equal to 0. So I get 0 equals negative 5 t squared plus 14t plus 3. Panic sets in. You're like, how am I supposed to know? Here's how this word problem is different than last chapter, right here. It's not in factored form. That's all that's different. So I'm going to write in big red letters because I'm scared of this step. I'm scared you're going to get in the test and go, I don't know what to do. So here it is in big red letters. You should do it in big red letters, or put little stars beside it, or highlight it or something like that. Factor. Our method of solving these things is all based on, what's that? You have a different equation? Change to mine. Yeah? Change to mine. Wow, between typing it up for you and making these flip charts, I came up with better equations. Remember I just said something about not realistic numbers? Once I saw these examples, I went, no, I'm going to go to stuff that's a little more realistic. On Earth, here are some mind-bending stuff on a Monday. On Earth, that number out front should be negative 5.
What about space?
In space, things won't travel in a parabola. But I'll tell you, On the moon, it would be like a negative 1.6 or something like that, or negative 0.8. No, that's right, negative 0.8, because of the different gravity. Yeah, good. That's where we want to be right now. It's like, whoa. So your initial one had negative 3 in there. Me being a physics guy, I was like, well, let's get the numbers at least what they are on the Earth. Around negative 5. It's actually negative 4.9. And double it's negative 9.8. I don't know if you've ever heard that number before. Negative 9.8 sort of rules our life on the planet Earth.
Does gravity get stronger the closer we get to the middle of the Earth?
Yes, but not by much. That is, if you took your scale from home and you took your weight at the bottom of a mountain and then picked up your scale and walked up the mountain, well, first of all, you'd probably lose some weight from the exercise. But let's imagine instead we were weighing a 100-kilogram weight, and you measure it at the bottom of the mountain, and then you measure the top of the mountain. Your scale might not even register the difference. You'd need a super accurate scale. But if you had a super accurate scale, when you went to the top of the mountain, it would weigh less.
A lot?
No, 0.1% or something. But as you got farther up and farther away from the Earth, it would start to change. Not as much as people think, though. Not to get sidetracked, but when you see people on the International Space Station floating around, they're technically not weightless. There is gravity. It's just that the space station's falling just as fast as they are. So then it looks like they're weightless. Think of it this way. If you were on an elevator that was 500 floors high and the cable let go and it just started dropping, you'd feel weightless. You'd just be floating around the elevator. Now, hopefully you'd be floating around in a panic going, this is not going to end well.
Wait, I thought the elevator would go like this and you would go like that.
No. If that thing if you were standing in an elevator, like, say this is me standing in an elevator like this, and the cable let go, holding the whole thing, and just totally let go, yeah? Then I would let go too, and it would just be free fall. You'd be doing exactly what the astronauts do, pushing off one side, whee! You'd be having a grand old time, but not for long, right? This can't go on for very long. So we need to, in our mind, if we're going to do the mental experiment, we'd need an elevator that was 800,000 floors high, so that we don't smash into the ground very quickly. But if that would be free fall. You'd be going the exact same speed as the elevator, so then you'd think you were weightless. You'd be floating around, pushing off the walls. Austin.
But wouldn't there be more friction between the elevator and the elevator shaft than between you and the elevator?
Yes. I'm just talking about if the cable let go and the thing just went free fall. Technically speaking, the side walls might slow it down, but if both of you were in free fall, that's what's going on with the astronauts in space.
How do planes not have no gravity? Wait, why are you not flying in planes? Like inside the plane, like what happens? Like what happens in the elevator? Why doesn't that happen in planes?
It could. If they do this sometimes for simulations for astronauts. They take a plane and they fly it way up in the air like this. And then they turn and they just let it drop like this. And so the astronauts get used of weightlessness. They get, I think it's 40 seconds or something like that. That's about the most you can do before the airplane has to go, okay, well, that's it, folks. I got to start coming out of it. So they do that exact thing with airplanes when they're training astronauts. No, these are great questions, folks. They're off the charts, amazing questions. Go ahead.
And the airplanes are going at the same speed, like you inside the elevator.
Yeah.
How come, like, when it's going like that, you're not like weightless?
Oh, as the plane flies along this way, let's say the plane was going 200 kilometers an hour. The air's going 200 kilometers an hour. The seats are going 200 kilometers an hour. You're going 200 kilometers an hour. And so everybody thinks you're just sitting still. Like when you're on an airplane, if the windows were all down, you wouldn't know really that you were moving. It's the same as in a car, right? When you're sitting in your car, driving along the highway, you don't really feel the motion per se. Yeah, like the car vibrates a little bit, but what should happen? In your brain, you go, if I throw a ball in the air, shouldn't it go flying into the back window? No, the ball's going 80 kilometers an hour as well. Everybody's going 80 kilometers an hour. I'll do one worse for you. The Earth is blasting through space. Like, it is moving. It's not just moving, spinning. It's spinning, but it's also going around here. And the solar system is going through the galaxy. We are moving. Does it feel like you're moving? No, because we're all moving. We're going the same speed as the Earth. And if you jump in the air, you go, don't I fly off the Earth now? No, you're going the same velocity as the Earth, so there's nothing to slow you down. Yeah. Different than if you throw something out the window of your car. So you take your McDonald's garbage and you huck it out the window. Yeah? It catches the air, and the air immediately slows it down. That's why it slows down. If you put your hand out the window, you feel the effect. You start to feel like, oh, if it wasn't for these windshields, this thing would be, the air would be pushing me back. They're great questions, and it starts right here. The journey along understanding that starts right here. But we need to factor. Here comes the factoring. I'm going to do it fairly quickly to try to inspire you in the sense that, oh, as long as I can factor, this is no problem. I'm going to pull off the -1. That's an extension of what I said about the negatives before. I said always take the negative off the front. And now I've extended it to say even take that negative off the front if there's no other number to take out. Like, it's just going to be easier to look at if you take the negative right off the front. Can it be done another way? Not an easier way. Whoops, I dropped a negative there. -5t² plus 14t plus 3. Then factor this disaster back to the beginning. Does it have a common factor? Is there a number that divides into 5 and into 14 and into 3? No. Does it have 2 terms? No. Does it have 3 terms? Yes. Is it simple or is it complex? Complex because that's a 5 out there. So now we're back to decomp. Here comes decomp. AC will be -15. 2 numbers that multiply to -15 but add to -14. I love the thinking. The things everyone said there were exactly the things you should be thinking. Like, okay, it's 1 and 15. Now hang on though. Is it -1 positive 15? Is it +1 negative 15? If you're not sure, watch what happens next. I'm going to take that to break that middle term up. That's all decomp does. That's the decomposition part. Is it takes this -14t and breaks it into just the right things. And technically now that's 4 terms, and we do factor by grouping. That's all decomp is break up that center term so that the factoring by grouping goes well. And if you're using window, I love window. No problem. Do window. Let's see, common factor the first set. Common factor the second set. And now I get my brackets, -1, 5t plus 1, and t minus 3. That's what we couldn't do last chapter. So when I typed up the test, I had to, instead of write the equation like this one, first line, I had to write the equation like the bottom line. Then you guys could do it after I did that. I can get my zeros now. 5t plus 1 equals 0. Or t minus 3 equals 0. If I solve this equation, I get t equals -1/5 or t equals 3. Which one's this? That's got to be 3. Yeah? The answer is, therefore, the diver hits the water at t equals 3. where's this t equals 1/5 coming from? Well, it's true. That is, if you take the parabola back in time, it hits the axis at -1/5. But for our answer, we're not looking for the negative time. We're not looking for when would the diver have jumped out of the water if we backed up time. And that's not what we're looking for here. So by creating a parabola to model the situation, we only really want this part of the parabola. We don't want that part of the parabola. So don't that freak you out when you get an answer from quadratics that isn't the one we're looking for. So the diver hits the water at 3 seconds. Now when I made up this question, this version of the question, I knew the numbers got a little stinky here, but I liked it. I liked it to go, okay, even if the numbers are a little stinky, I can handle it and get the answer here. Because my next question is, without looking at the numbers, what do I do to find that t value of the vertex? Just average those two. So what I'm going to do is go t, and I put a little v there for vertex. That's what I do. To remind myself I'm looking for the t value of the vertex. I'm just going to add these two things together. So it's 3 plus -1/5 divided by 2. And I know that's a big mess, so I'm going to go to decimals. 3 plus -1/5 is 2.8. Divided by 2 is 1.4. So not too crazy, the numbers there. 1 decimal place. Like I say, when I made this up, I'm like, are the numbers too crazy here? And then I decided, well, no, they're not bad. 1.4. So you type in 3 plus -1/5, and you divide that by 2, 1.4. I'm almost home. They want the maximum height. I've got the time for the maximum height. How do I get the actual maximum height now? Just sub it in. And you can sub it into here, into this vertex one, or you can sub it into the original one. To me, the original one looks pretty tasty. I get it to sub it into, so it's whatever one you want. So then height at the vertex is -5, 1.4 squared plus 14 times 1.4 plus 3. Now, friends, I'm a little worried about this from the test standpoint. So I just wanted to say to you, be prepared that the numbers might get just a little hairy. Or my other choice is to make the numbers not very realistic. So when you get your answers, you're like, oh, well, I don't think that makes a whole lot of sense there. When I type that in, I get 12.8. Did anyone else type it in and get 12.8 meters? This diver jumped up to 12.8 meters? 37 feet? Yeah, see, this is the problem. In the effort to make the numbers all work out nicely, sometimes we're stuck with numbers that don't make a lot of sense. Having said that, if a diver jumped off a diving board, jumped through the air, we could find the exact equation. They might be nasty decimals all the way through, but we could find the exact equation for them. And we'll get to that level maybe in grade 11. Question? Yeah, see, the ones before we just looked at, t minus 3, and went, oh, what number could t be to make t minus 3 equal to 0? And we just picked it off out of there. But if the factor's a little more complicated, then we're going to have to take that out as a separate equation and go, okay, I want to know when 5t plus 1 equals 0. When does this factor equal 0? And I have to solve a little equation there. That's fairly new. Most of the ones that we've done before, you just looked at it and you could just pick off the number. This one, you'll have to make that factor into an equation that you'll solve. A two-step equation. Yeah. What makes it 0? Well, I could stop there. I really could. I could be like, there, that's all you're going to do. Tonight you're going to go take a word problem with an equation, and you either set it to 0 and factor it, or then you'll take that and find the x value of the vertex and sub it in. Yeah. But don't let the upsetting numbers fool you here. There's nothing new here from a conceptual standpoint. just me going, well, let's just play around and try to balance this realistic numbers versus decimal answers type thing a little bit, like. Questions there? More time? The area of a rectangle is given by the equation a equals 6x squared plus 5x plus 1. What? How can that be? What's the equation for area of a rectangle? Straight out of grade 5. Base times height, or length times width, however you write it. So I'm going to write both. He said base times height equals length times width. This isn't a base times height, or it isn't a length times width. I don't have two things multiplied together here. What could I do to this three-term trinomial to turn it into two things multiplied together? The thing. Factor. Like you call me over at this test, and you're like, Mr. I don't know what to do with this one. 96% chance I'm going to say, try factoring it. Like the chapter's called factoring. Good chance you're going to have to factor in the question. You're like, well, how am I going to know long term? I'm like, let's worry about that in future chapters. For now, let's see if this thing factors. And again, I chose one fairly spicy, so it wasn't really obvious. Well, let's do Friday's lesson again. Does this have a common factor? Is there something that divides into 6, into 5, into 1? No. 1, yeah, you could factor off a 1. But if it's not a negative, it doesn't really change the whole deal very much. Next. Is it 2 terms? No. It's 3 terms. It's 3 terms. So it's either an easy trinomial, a complex. It's a complex. Of course it's complex, because I'm trying to teach. So AC is 6. She says it's 2 and 3. 2 times 3 is 6. 2 plus 3 is 5. If you haven't got great at those yet, it's time to panic. It's time to get into gear and get these things narrowed down. So I take 6x squared, and I break it into 2x and 3x, and then I do my common factoring. 2x, 3x plus 1, and 1. Oops. AC 6. Now that this is factored, do you see the length and width now? This is the length, or maybe it's the width. And that's the width, or maybe it's the length. Rectangles, they're sort of interchangeable there. So, here's my conclusion. Therefore, length equals 2x plus 1, and width equals 3x plus 1. Now it is two things multiplied together. So once you determine the expression for length and width, I did that. There's length, there's width. State the length, width, and area if x equals 4. If x equals 4, length equals 2 times 4 plus 1, which is 9. If x equals 4, width equals 3 times 4 plus 1, which is 13. And if x equals 4, I'm looking for two answers here. Not two different answers, two ways to get the answer. How would you find the area if you knew x was 4? You could just go 9 times 13, couldn't you? You could take the 4, put it in here, and you'd get 9 times 13. Or you could put the 4 in the original equation and multiply that all out. I'll do the obvious one here that she said is just 13 times 9. But again, all that subbing could work. 13 times 9, 90, and 27, 117. Now, friends, I said I was going to do better on communication marks this chapter. One thing was equal signs. The next thing is units. Those are the two. I won't just circle them. I'll actually take marks off if you don't get the units here. So this is 9 centimeters. This is 13 centimeters. And this is 117 centimeters squared because it's an area. Yes? Oh, there's a spicy one on the test like this. So what are we going to write on the top of our test? We're going to write common factor first as soon as you get your test, but underline the factor. Go, listen, when I get to a question that I just don't know what I'm supposed to do, maybe I'll just try factoring it first and see what I get after that. Because this one is a very scary question until you realize, oh, I could factor it into two pieces. And those two pieces would be the base and the height, or the length and the width. What questions do you have? You got one more? Yep. Last one? Oh, and I got a list of stuff on the board to talk to you about, so you can preview that if you're bored during this. Is this a different equation than yours? No, this is the same equation as yours this time. It's only the other one. -5. I'm a physics person. You at me, I'll put -5 out there every time because that's very close to what the Earth factor is. Yes? A rocket is launched from the top building and falls to the ground. Its path is approximated by this relationship. After how many seconds will the rocket hit the ground? Is it the same question as number 1? Like, it really is. Because as much as word problems are scary, in this chapter there's only two things I can ask. When does it hit 0? And what's the max? So here we go through all the steps again. A. Set h equals 0. We want to know, when does this equation come out to be 0? Then we'll know when the rocket hits the ground. What should I do to this equation to help me factor it? Yes? Again, the chapter is called factoring. It's going to come down to factoring. Is factoring the only thing in the world? No, I'm going to show you other stuff. But this chapter, factoring is where it's at. So here it is in big red letters again. Factor. And then back to Friday's lesson. Here we go. Does it have a common factor? Yes. What number divides into 5 and 5 and 30? 5. Take the negative. That's just my personal advice. You're going to find these easier. If that first term is negative, take the negative with you. Because what you get after you take out -5 is t squared minus t minus 6. And if you're right with me, if you've been keeping up and you know what's going on, as soon as you see that, you're like, that's nice. You might even take a break. You're like, I'm going for a cookie. I'm going to go, yeah, this is no problem. Yeah? Is it 2 terms? No. Is it 3 terms? Yes. Is it simple or complex? Simple. Good. It's simple. So we go, all we need, I don't even know if I need to write anything down. I need 2 numbers that multiply to -6, but add to -1. It's definitely 3 and 2. And I like this thinking too. When people get to the point with factoring, they go, well, I know it's 3 and 2. 3 times 2 is 6. 3, and then which one's the minus though? -3t plus 2t? Yeah, you're like, this is all you got, is play around with it until you get the right number? Yeah. So therefore, t equals 3 or t equals -2. That one's less upsetting because you don't have to do any work. You just look and go, what numbers make these factors 0? But what's my sentence then? When does it hit the ground? At t equals 3. This -2 is mysterious, but if you want, that's when the model rocket would have hit. If we went backwards, that's when it got off the ground or something. You know what I mean? Like, you can see how the parabola would have that in it, but that's not the t we're looking for. We're looking for t's that are positive, the positive t's. Therefore, the rocket hits the ground after 3 seconds. Incidentally, we are right on top. You ever watch a baseball game where somebody hits a home run and they go, that would have went 462 feet? You go, how are they figuring this out? This, almost exactly this. We're very close to being able to do that calculation. We'd have to use -4.9 instead of -5. That initial value, that y-intercept would be like however height the ball was hit at? Maybe we'd need a graphical overlay to see what the equation was, but we're very close to being able to do that now. All right, that's fine. B, maximum height. Maybe you need a little picture now. You're like, okay, hold on here. I know that. I got the zeros now. What to do now? To get the maximum height, because it's 2 steps. What's the first step? Yeah, find the t value of the vertex. I really like putting a v there. It really helps me to think going, okay, I now want the t value of the vertex. That'll be halfway between the zeros. So 3 plus negative 2 over 2. And 3 plus negative 2 is 1. I get 1/2 here. You want to go 0.5? I think decimals are allowed here. It's only going to be 0.5s anyways. Now I've got the t value of the vertex. How do I get the maximum height now that I know the time? Just sub it in, yeah? Sub t equals 0.5 into h. So I get h equals negative 5 times 0.5 squared plus 5 times 0.5 plus 30. I'll try and do it in my head, and then you compare with what you get off your calculator, okay? That's 32.5 over there. That's a quarter, negative 5 quarters, negative 1.25, 32.5. 31.25? I don't know what's right. No, it's 30.25, isn't it? I'll check with someone in a second. I'm just playing around up here on the last example. Did anyone type it in? What'd you get? Am I totally wrong? I was right the first time. 31.25. Shouldn't have doubted myself. $31.25. Therefore, the max height is 31.25 camels, wagon wheels, meters. I'm going to take communication, not many, a little bit of communication marks. You'll see me circling red, you're like, ah. Units and equal signs. Yeah, we'll start there, and we'll upgrade from there. Any questions about that? Nuh-uh. And I've showed you the word problems. I've showed you. When does it hit the ground? What's the max value? And then the spicy word problem, where if you don't know to factor, you're in trouble, right? So you got to factor to do those area ones.